Hello, everyone, and welcome to the Exam 2 review. Now, let's jump right into it. So, the first question is asking us to draw the VSEPR structures, labeling the angles, correctly showing the wedges and dashes, and you must state the molecular geometry, show every electron, blah, blah, blah. Okay, so your first step is to actually draw the Lewis because you can't draw VSEPR without drawing Lewis. So to figure out Lewis, you must know the total valence electrons of your molecule. I went ahead and gave you those already because you should know how to calculate that. Okay, I'm not going to hold your hand while you do that. You should know it's 32. Okay, so your first atom in the formula is typically your central atom. So you're going to start with drawing the skeleton. Okay, so this consists of drawing the central atom, connecting it with your other atoms that are bonded, and then instantly drawing lines that connect them. Okay, so this is how I draw Lewis. It's a little different and quite a bit easier. So if you want to pick up some things from me a little bit or two, low key you should do my method because my method's obviously the best method, not to brag. Okay, so I do it, and you know how some people like to divide by two, subtract how many lines you drew? No, this is a drawing class, not math class. You're just draw the dang thing. Okay? I need 32. I can't have less and I can't have more. I currently have 2, 4, 6, 8. Okay? You're going to start by drawing or putting dots on the outside atoms first and then put it, if you have, they're all filled up, put it in the central atom. That's how this works. Okay. So I have 8, right? Here comes 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Boom. Now, it is an ion, so you do have to put them in brackets on whatever the charge is. Okay? You should know the molecular geometry. If this is 4 things the central atom is connected to, for 4, it is tetrahedral. Now, you should also know the VSEPR of tetrahedral. You start with your central atom. Okay, now I have little stickers because I'm cool like that. Put my fluorines. Put fluorines electrons. And remember, it is an ion, so put them in brackets. Now, you're going to put your angles. Okay, so you should know the angle of tetrahedral. You had to memorize this. What is the angle from this atom to this atom? You should all be saying 109.5. Bam. Now, on the exam, we'll actually be asked another question. What is the polarity of this molecule? So, the polarity chart will be given to you with all the little numbers. You should know that fluorine is 4.0. And then you're going to subtract it with beryllium, right? But I'm going to show you a method that you don't have to do it, and you shouldn't do it. You should not be doing math when drawing, okay? So you can simply just figure it out mentally by doing what we refer to as polarity arrows, okay? I swear, if one of y'all do math, um, you'll be shamed because you can easily just figure it out, okay? It's not that hard, okay? You should know that fluorine is more electronegative than beryllium. So that's the direction the arrow goes. It points at the more electronegative atom, okay? So you have all these arrows pointing towards the fluorines, okay? Now, these three arrows are all pointing in the actual same direction. So you would show the vector of all these three. That vector is simply pointing down. And then you still have this vector. So if both of these two arrows that I drew are equally pulling in the same opposite direction, there's actually no pull, meaning it is non-polar. Do you see what I did there? Okay, so if here are the vector arrows, there's no pull, it is non-polar. Okay, didn't think about it that way, did ya? Okay, if they're equally pulling the exact same um, pull, then the molecule isn't going anywhere. Okay, it's like a tug of war. Okay, you have two strong people, both equally strong, both pulling in opposite directions. No one's gonna move. It's non-polar. So that's that. That's the first question. Let's move on. Okay, so remember that typically the very first atom is your central atom. Besides hydrogen, we all know that. So iodine is your central atom. Okay, then you're going to connect it with the atoms, draw lines. This is your skeleton structure. Okay, I need 34. Can't have more, can't have less. I currently have 2, 4, 6, 8, right? So here comes 10, 12, 14, 16, 18, 20, 22, 24, 26, 20, 28, 30, 32, and here's 34, right? All the octets are full, so what's left is to put them in the central atom. Okay, don't forget this is an ion. Now, you should know what the electron geometry is. Not molecular, electron. Electron geometry is how many things it's attached to. So you have 1, 2, 3, 4, and 5. So if it's 5 things, you should say trigonal, bipyramidal. Cool. The molecular geometry, you should actually all be saying seesaw. You should know that. I can't help you. This is strictly memorization. Okay? You have to focus, lock in. It's memorization. I can't really help you. I made flashcards. Okay? That's the only best I can do. Your seesaw, you should be drawing, looks like this. My handy dandy little stickers. Okay, put these dots. And then you have your lone pair electrons. Kind of looks like that. Don't forget it's an ion. Okay, so now it is your angles, okay? So it is very important to know the tendency of your lone pair electrons, right? So the charge on these two electrons is negatively charged, correct? And then you have a bunch of electrons on these ones. So if this is negatively charged and these are negatively charged, they're just going to want to repel. So this is your lone pair repulsion. This causes this atom, oh, why did I duplicate it? This causes this atom to be slightly bent. It repulses it, right? Because let's do it to this one. Okay, and you absolutely must draw it bent. If you do not draw it bent, you lose points. Okay, so if this was before a straight line, right? It was a straight line before. You know, straight lines to be 180 degrees. It is now less than 180. Before, this looked like a perfect right triangle. Right triangles are 90 degrees, but now it is less than. And then this one is your 120, but now it is less than. Okay, so let me point out a few things. Your up and down is considered your axial. Or is it EL? I don't know. I don't know how to spell. Axial. Okay. Your horizontal is your equatorial, right? Just think like the equator. Your equator is horizontal. This is your equatorial. So these two atoms are in line with this one, right? Horizontal is your equator, and then up and down is your axial. So when we refer to bond angles, we say axial to axial or oxygen to oxygen. We might say axial to equatorial. This is your oxygen of fluorine having less than 90, or your equatorial to equatorial being 120. Okay, so you might switch it up. You might say, specifically give me equatorial to equatorial, not all of them. Or, I don't know what you can do, just be aware of that, of the terminology. Okay, that's pretty much it. You don't have to state axial, you don't have to state it's equatorial, just draw it like this. Give me everything. Okay, now let's figure out its polarity. So, I'm going to show you all the vectors, okay? You know that fluorine is the most electronegative. So it points in these. Oxygen is slightly also electronegative, so it has a smaller polarity arrow. However, your lone pairs is gigantic. It has the most polarity. It has pull. The whole molecule is being pulled towards the lone pair. Getting so much pull, in fact, it literally causes lone pair repulsion for it to be bent. So the whole molecule is actually be pulled in this direction. So if it has pull, it has polar. tendencies. Okay, there's no need to do math. There's no need to do 4.0 minus whatever oxygen is. I think it's 2.5. I'm pretty sure. Or maybe it's 3.5. I don't know because you don't even have to know it, okay? It's going to be given to you. If you desperately want to do math, please don't do math. Okay? Know the tendencies of vector arrows. This is so important. Okay? Next question. Okay? Your central atom is selenium. Then connect them with chlorines. Okay, I need 42. Can't have more, can't have less. I currently have 2, 4, 6, 8, 10. So here comes 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42. Okay? What is the electron geometry? Not molecular, electron. Electron geometry is how many things? So it's 1, 2, 3, 4, 5, 6. That's 6 things. You should all be saying octahedral. Now, the molecular geometry, it's something square. Can anyone tell me what the actual name is? Is it square? Square what? Someone tell me. Square pyramidal. That's what it is. Okay, gotta memorize it. So to draw a square pyramidal, it looks like this. I like to put my electron at the bottom. My handy dandy stickers, because I'm cool like that. Okay, chlorines, chlorine, chlorine. Put your dots. Now, don't forget, it is an ion. Do it for this one too. Okay, now let's do the angles. So, all octahedrals, every single one, octahedral, regular octahedral, square planar, and square pyramidal. Everything. All angles are 90 degrees. Okay? From all around. The whole shebang, all around. That's why it has a little tail. All around is 90 degrees. But the second you see lone pairs, right? Remember, this is lone pair repulsion. It is less than. Okay? There's only one exception. Okay? So pretty much every single time you see a lone pair, no matter what it is, every time you see a lone pair, put less than. Every single angle less than of what you think it actually is. Besides your linear trigonal bipyramidal. Okay? It has lone pairs like this. Remember how I talked about polarity arrows? It's the same thing with your lone pairs. So it has this polarity arrow, right? And the vector of these two arrows simply point in the middle, right? And then you still have this one. So if these two arrows are pulling in opposite equal amounts, right? It's like a tug of war. Two people, they're both buff, they're both equally strong. There's no pull. It is non-polar. Okay, so this is the only one. So if this is a straight line, it is 180, not less than. It is 180. Okay, so if all of these are pulling towards the chlorines, right? Because chlorine's more electronegative than selenium. However, this lone pair is huge. The polarity arrow is gigantic. So if there is a pull, it is polar. Okay, remember, just for the blue guy, it is non-polar. I swear, if I see any of you guys doing math, I will scream. Oh my gosh, mid-exam, I'll literally do it. No, I won't. Next question. Okay, last example, a Vesper. Iodine in the middle, surrounded by 3 chlorines. Okay, I need 28. Can't have more, can't have less. I currently have 2, 4, 6. Okay, so here comes 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. Okay, so what is the electron geometry? Remember, electron geometry is things it's holding on to. So it's holding on to one chlorine, one chlorine, one chlorine, that's 3, 4, 5. 5 things. 5 things is trigonal bipyramidal. I don't really know how to spell. Hopefully it's right. Yeah, whatever. So you should know what this is. Hopefully it is your T shape. Okay, I can't help you. This is memorization. You gotta sit there and lock in. Your T shape must be drawn like this. Okay, iodines, your chlorines. Well, it's actually more of an angle, so I'll like draw better. More or less looks like that. Okay? Okay, so this is not an ion, so it doesn't have brackets. Now, what is the polarity of this molecule? Remember, if all of these are baby tiny pointing at chlorines, you have a vector of these two lone pairs, okay? They're both pulling, the vector is gigantic. It's pulling over here. So if one has more pull than the other, it's automatic. It has pull, so it's polar. Okay. Even though this arrow is pulling in opposite directions of this arrow, this one outweighs more. It's gigantic. It is a lone pair. It has pull. It has polar. Okay, that's it. And I swear, don't be doing math on this part of the exam. You don't need it. And that's it. Let's move on to the next question. Okay, for this part of the exam, we'll be doing resonance. And resonance is the exact same as Lewis structure, but you notice that every time you draw Lewis, you can draw it many different ways. So each time you draw it, the same molecule, it has actually different chemical properties, depending on how you draw it. But by definition, resonance is the moving of electrons. Okay, so let's start by drawing the Lewis structure of one of them. So he's not going to be given this little cheat sheet, but it's the same thing you've been doing, where the first atom is your central atom, and then you just connect them. So there's 24 total, and we currently have 2, 4, 6. So here goes 8, 10, 12, 14, 16, 18, 20, 22, and 24. So antimony doesn't have an octet. So it's going to steal from a neighbor and make it a double bond. So that it's happy. It has an octet. Okay? So I want you to, or actually, before that, um, typically resonance is that if this atom can have a double bond, why can't this one or this one? So resonance is moving of electrons, not atoms. So if you just rotate this, you're moving the atoms around, not the electrons. That's not resonance. Okay? So it's easier for resonance if you have a double bond, right? You just move the double bond, make this one a double bond, make that one. Okay? So I told you some ways. There's 6 different ways, not 4. And I want to see if you can do all 6. So go ahead and pause this video and see. Okay? So 5, 4, 3, 2, and 1. You should have already paused the video, figured it out. And here are the answers. Okay, let's dissect this. So there's a couple of things about resonance. There's 2 most crucial ways, okay? If your molecule is neutral, right? It's not an ion. It must end neutral. This is crucial, okay? This is how to check your work, see if you're doing things correctly, okay? And then there's one other important thing. Resonance does not follow octet, typically, okay? So if you ever get stuck, only have one atom, okay? Not all of them, just one atom, not follow the octet rule in case you get stuck. So I'm going to point out this one, right? Antimony doesn't follow the octet, but all of the other ones do. So you can see antimony has 2, 4, 6, 8, 10, 12 electrons. Doesn't follow the octet, but we call this still resonance stabilized. Okay, but only one. Just have only one atom not follow the octet, and it still works. Okay, so next up is to figure out which one is most significant. So we do that by doing formal charge. Definition of formal charge is your valence electrons minus the lines minus the dots. So let's look at oxygen. Oxygen's valence is 6 minus 2 lines minus 4 dots. That's 0. Sulfur is 6 minus 1 minus 6, negative 1. So this atom is negatively charged. Fluorine, 7 minus 1 minus 6 is 0. Antimony is 5 minus 5 lines minus 0 dots. That's just 0. Okay, so this whole molecule, well actually, let me check that. Let me check that out. There's 4 lines. See, good way to check. Remember, if you start neutral, you must end neutral. It's positively charged. Okay? See? That's why I'm here. Okay. Molecule neutral. This molecule became neutral. Okay? Good way to check your work. Let's keep going. So, this oxygen, 6 minus 1 minus 6 is negative. Negative. This one is 0. It's the same as the oxygen one on the left. It's the same one. 0. Oh, 0. Antimony is 1, 2, 3. 1, 2, 3, 4. All right, so 5 minus 4 is positive. So now the oxygen's negative. This antimony is still positive. Okay. Negative. Negative. The fluorine is 7 minus 2 minus 4. This is positive. And antimony, 5 minus 4 lines is positive, right? So this whole molecule is still neutral, right? This positive cancels out with this, or this negative cancels out with this positive cancels out with this negative. The whole molecule is neutral, and this must be important. Okay, this one is negative, or neutral. This one is neutral. This one, neutral. Okay. Antimony is 5 minus 5 lines minus 0. Neutral. Interesting. Let's keep that in mind. Neutral. Neutral. Remember I said this one was positive. This antimony is 5 minus 1, 2, 3, 4, 5, 6 lines. No dots. Positive. Or negative, I meant. Sorry. Negative. Right, quick math. This one is negative. Negative. This one is neutral. Your antimony should be 5 minus 3 lines. This is plus 2. Okay, so to figure out which one is most significant, you're going to look at all the formal charges, right? Well, you can see this one is our answer, but I want to point out which one is not your answer. That'd be this guy. Which one is the worst, right? Antimony doesn't follow the octet, it has the highest number of formal charge, so he might switch up the question. Which one is absolutely the worst one, instead of which one is most significant, okay? I don't know, he could do that in case he wants to. So it's this one. Reason being, all atoms are neutral with formal charge. That's it. Okay. Let's move on to the next question. For this question, I want to cover a couple of things before we even start this question, okay? So let me just open up a blank canvas and I'm just going to draw a random, let's see, random molecule, okay? Perfect. I want you to tell me the hybridization of your central atom. You have a couple choices, sp, sp2, sp3, sp3d, sp3d2. Okay, hybridization is things it's attached to. Okay, but first off, I want you to treat each letter as just a single digit. Okay, one. So just treat this S as one, a P as one. One plus one is two. These are your things. I promise you it will make sense. Okay, just stick with me. Okay, one plus two, three. One plus three is four. One plus three plus, just pretend a D is one. It's five, and it's obviously six. Okay, so how many things is this sulfur atom attached to in this molecule? Okay, you should be saying one, two, three, four, and five things. So this is your hybridization, sp3d. Okay, now bear with me, let's come back to this. Okay, so with all of these questions, right, to solve the energy diagram and to figure out the contour diagram, you first must draw the Lewis structure. You absolutely have to. Okay, so let's start by drawing the skeleton. There's 6 bromines. Right, and let's start with the valence. Let me just see real quick. Okay, valence is 48. Right, okay. So we currently have 2, 4, 6, 8, 10, 12. So here goes 14, 16, 18, 20, 22, 23, or 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, and here's 48. Okay, so what is the hybridization of this central atom? Right, it's things. There's 6 of them. So what's that answer? You just simply count. In case you forget, the order, you don't actually have to memorize it. You just count them as digits. It's, oh, you know what? To always be SP, okay? Right? SP3, D, and then something, okay? You just count. S is 1, P, 3, plus, you need this to be a 2. Okay? You don't have to memorize this. Just count each digit as 1, and you just simply figure it out. Okay? So this tells us our hybridization. I'm going to refer to this as our rule of thumb. Okay? So this tells us how many boxes must have electrons. Must, okay? I must have electrons in the S box. I must have all three P boxes full, and then I must have two D boxes, okay? So this is the energy diagram. Your energy diagram will always be of the central atom, always. It is the ground state of selenium, okay? Now, your box diagram is also strictly valence electrons, okay? So selenium is in period number 4. So it has a 4s, a 4p, okay? You could find selenium on the periodic table. Its valence should be in group 4. So I'll just start with 2, 1, 2, 3, 4, right? You know that? Okay. So you should know how to do it. I'm not going to really walk you through it. You should figure out the valence electrons of selenium. Okay. Hopefully you're not having any trouble with that. It's so there must be 2 electrons in the D box. So you can see which 2 electrons we should excite, right? It's going to be these 2. This one should go first because it's higher in energy. And then this one is going to come in and do that, okay? And then here's what's left over, okay? So your hybridization tells you not how many electrons must be filled up, right? It tells you at least 1 electron must occupy that box, the S box, the P, and the D. Just for reference, I'm going to continue labeling these. 4S, 4P, and your 4D. Okay, so now you're going to take all the boxes you just are going to fill up, and then you're going to hybridize them. Okay, this is also very, very important. When you hybridize, your hybridization orbital 1, 2, 3, 4, 5, 6 must, absolutely must be above the S but below the P, okay? Not necessarily in the middle, but slightly above the middle, okay? I'd say like 3/4 of the way, okay? If anything, could just be a slightly bit higher, right there, okay? This is crucial. This just tells you that this hybridization is in the energy diagram, okay? This also might impress him, that you know your stuff, that you know that it's higher than the S, lower than the P, okay? So you take all those electrons, separate them, okay? And then here come your bromines. There's 6 of them, okay? This is the electron configuration, valence of bromine. Bromine is in the 4p. No, 3p. My bad. Okay. This one electron that doesn't have a pair is going to pair up. And this forms your sigma sp3d2 bonds, okay? And that's pretty much it. That's all you have to label within the box diagram, okay? So just please remember that whatever you're hybridizing, it must be above the S but below the P, okay? Slightly like 3/4 of the way, okay? And remember that all the energy diagrams and the whole thing, even your bromines, it's strictly valence, okay? Don't forget this. You also have to label where the bromine comes from. So, let's move on to our contour. Your contour, oh, just real quick, ground state, excited state of selenium, just in case you wanted it. You don't have to label that, but I think that's important. Okay, so your contour diagram is essentially the same as the Vesper. Okay, so I pretty much drew it as the Vesper, right? It was like this, essentially in those specific angles, okay? But your contour diagram, instead of wedges and dashes, it's kind of like little balloons, okay? For a single bond. So selenium, and draw its balloons, okay? Not an artist, please don't judge, okay? Now, bromine also has a pair of balloons. Wow, looks like a little flower. Okay, so here's where your electrons live, in these little spaces that connect them. They are your sigma sp3d2, and you must have to do it for all of them. So tedious, but it is necessary. Okay, then you have to label, okay, so if pretty much, where do these electrons occupy? Okay, because they're still there, they still float around where the bromine is. So wherever it's at, you still gotta put 3p. I just put it right next to the bromine because those electrons can go inside of this orbital, they can go into this orbital, kick out the sigma bond, and then replace it. Those electrons, they simply just fly around into its bubble, okay, its balloons. So just put 3p, bam. And the last thing that's left is to do your angles. So what is the angle from here to here? This is your axial, right? This is 180. Your equatorial to equatorial. This is your 90. Perhaps your axial to equatorial. This one's also 90. Remember, can't help you there. You must memorize those. Bam, there's my contour. Okay. So, bromine, fluoride ion. Let's start by drawing the Lewis structure. So bromine, middle, connected by 4 fluorines. Okay, you should have counted the valence as 36. We currently have 2, 4, 6, 8. So this should be 10. I'll color, stay consistent. 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, and here is your 34 and 36. Okay, a little tricky on that one. So, what is the hybridization of your central atom? Remember, it's things. It's connected with 4 fluorines and 2 different lone pairs. That's 6, right? So that's the same thing. sp3d2, 6 things. Okay, so this tells us that there must be at least one electron occupying the S box, all the 3 P boxes, and 2 in the D boxes. Okay, but let me show you something different if it's an ion. Must be crucial. If it's an ion, you have to follow formal charge. So the formal charge of this fluorine atom, remember, 7 minus 1, minus 1, minus 6, 0. Okay, that goes for all the fluorines, it's the exact same. Your bromines, remember bromine is also 7, minus 1, 2, 3, 4, minus 4, that should be minus 1. Okay, so because this whole thing is in brackets, right? Negative 1. But when you do the box diagram for an ion, it's no longer the ground state of bromine. It's the ground state of bromine ion. This is very, very important. Okay? You may have not covered this or maybe forgot. Okay? All right? It's the ground state of your central atom. Your central atom just so happened to be negatively charged, meaning it gained 1 electron. So the valence of bromine, right, is this 2, 3, 4, 5. Okay. So bromine is in the wait, did I say 4 or 3s for the other one? So sorry. Oh, just change all these 3s to 4s. That's my bad. I just looked at the periodic table. That is my bad. Just like the periodic table. Okay. So, right, this is the valence of regular bromine. But this bromine gained an electron. So you just simply add one to it. Okay. Now, let's go back to our hybridization. It's these two electrons that get excited. So this one will go first, get excited, and then this one, right? Because they're higher in energy. They're not going to steal this one because it's so low in energy. Why would you do that? It would require a crap ton of energy just to excite it. When this one, it's right there. It's close, it's nearby, it can easily just get excited. Okay, so let's see what we have left. We should have these two, and then those left, so it's like that, and then those two. This is your excited state of bromide, not bromine, bromide. Okay, then you're going to take all these, we're going to hybridize them. Remember, it must be 1, 2, 3, 4, 5, 6, because we circled 6 boxes. Just remember, above the S, below the P, almost halfway, but slightly above. Okay, so the ones we circled 1, 2, 3, 4, 5, 6, 7, 8 electrons. So let's put them in our hybridization. 1, 2, 3, 4, 5, 6, 7, 8. Okay. What are these guys called? These are your lone pairs. Then, here come your fluorines. There's 4 of them. Your fluorine occupies the 2p. Okay. This single unpaired electron will come and pair up. There you go. But this whole thing is the sp3d2 orbital. Even the lone pairs occupy that orbital, but these are your sigma bonds. Okay, so there you go. There's our contour diagram. Now our contour diagram follows the VSEPR. Does anyone know the VSEPR of this one? You should be saying T-shape. So you're going to follow the same layout as the T-shape of the VSEPR. Bromine. Okay. Bromine has its balloons. Ooh, that was a sharp balloon, the first one I drew. And then fluorine has its balloons. Okay. And then these are your lone pairs. They occupy the sp3d2 orbital. Okay. Sigma sp3d2. Remember, where do these electrons occupy, right? They still float around. So you just simply put it right next to fluorine, 2p. That's it. Okay, time for atom, or the angles. Okay, what is the angle from the top fluorine to the bottom fluorine? Okay, think about it now. You have lone pair, repulsion, less than 180 degrees. So, and then here to here, less than 90. Okay, so unlike Vesper, you know how essentially it becomes kind of bent. We don't like to do that for contour because it kind of looks just messy. So you absolutely can, you won't get wrong if you do bend these fluorines because of lone pair repulsion. But typically we don't like to do that because it's the contour diagram is its own separate thing and you don't want to have it too messy. Okay, so we don't typically bend them. That's it, that's for that one. Okay, now there's one take about this stinking question you must be paying super close to this question, okay? He will give you this question, and I'm going to teach you something actually completely different from what he is saying, okay? And this only refers if your Lewis structure has a double bond or your central atom has a double bond, okay? I'm going to teach you something completely different he did not teach. So I'm just going to draw the Lewis structure for you. Okay, that's the Lewis structure. And remember, all these have lone pairs all around. Okay, you know the deal by now. Okay, your central atom. I first want you to tell me the hybridization. It's the same thing, I promise. But treat this as one thing. Okay, a double bond is one thing, not two separate things. So this central atom is carrying 1, 2, 3. So if it's 3, what is that? You should be saying SP2, right? 1, 2, 3, 3 things. So that's the hybridization they occupy, the orbital. Okay, so let's see. Carbon, carbon's valence is in the 2s, 2p. You should know how to do this. I'm not going to hold your hand. Okay, there's only 4 electrons, just like that. Okay, now this only refers, so this is how I'm going to do it, okay? I only show my work for 1/2. If, pretty much, if there's more than one central atom, okay, I only show my work for one of the halves. So I'm going to do the ground state of left carbon, okay? I would do the same because if you do both at the same time, you're just going to get confused. Okay, so this is where I differ from one he differs. Okay, you need um, electrons to occupy one S box and two P boxes. But if the central atom is a double bond, I want you to circle your excited state of left carbon from right to left. I'll repeat it, right to left. Okay? Remember, one S box, you're going to circle right to left. Okay? I know, bear with me. Okay? Um, wait, this one shouldn't. Oh, just going to fix this real quick. Okay, so what I circled, remember, your hybridization is above the S, below the P. So I circled three things because my hybridization told me three things. Okay, but I circled from right to left, even though this one is empty, right? It's empty. So you're going to split up those electrons. There's the ones I circled is three, so I'm going to split them up. One, two, three. Okay, and this one is still left up there. It's one. Now there's a reason, okay? Bear with me, okay? This occupies the sp2, and this is the 2p. There's a reason. Reason being, when you draw a pi bond, your pi bond is in the shape of a p orbital. So if you do not have an electron in the p orbital, this is your pi bond, okay? If you're saying your pi bond that gets shared is in the sp2 orbital, you're wrong. That doesn't work like that, okay? It's a P shape, not an S shape. There's a difference. So whatever you do, do not touch this top one. Do not do it. Okay, remember, circle right to left. That's what you're circling. You're circling one S and two P's. Right to left. If you have any questions, please let me know. Okay, so let's label this. This is your pi bond. Then, if this was the left carbon, this one will be the sigma bond of the other carbon atom, and then these two will be the sigma bond of your chlorines. Okay, so you don't have to show your work for, or actually let me just show you real quick. Okay, if I were to draw the left one, so see if it makes sense, okay? So this is the, I'm just going to skip to the excited state of the right carbon, okay? Same thing that already gets excited, right? Pi bond, 1, 2, 3. Okay, so if you have 2 times the chlorines, right? Cut it in half, 2 chlorines. Okay, this one is going to bond like this, bond like this. This one is your pi bond. Okay, 2 times the chlorines. This one's going to bond like this, and then these two are going to come together to form your carbon sigma bond, and these two pi electrons are going to come together to form your carbon pi bond. That's how it works. So actually, do show your work for the right carbon, but you only have to show your work for the excited state of the right carbon. Okay, so actually do it like this: ground state of the left, excited state of the left, and then you only have to show your work for the excited state of the right. Okay, and then do this little thing to make sure, see if it makes sense. Okay, so this will be on the exam. This one question stumps everyone every year. Just please, please, please circle whatever you're hybridizing right to left. Okay. Let's draw the contour diagram. It's the same as the Vesper. Okay. Should have your carbons in the middle. Okay. Let me draw it somewhat bigger. Okay. Each of its carbons has a pair of balloons. Okay. Then it's being shared with a chlorine balloon. Bam. Okay. And then you're going to draw the pi bond. So your pi bond has its own special pair of balloons. Okay. How I do it is, I know he draws it a little differently. You can refer to the notes how he draws it. This way it's a lot easier. You just draw a bunch of tick marks. So I got full credit. Okay. But this is your 1/2 pi, right? Because it only occupies one electron. This is your other 1/2 pi. Here's your other electron. And together, both of them combined make 1 pi. That's how that works. Now, I don't know if he's going to be picky, but yes, it is crucial that if you put both the dots on the top and the top, that's not how that works. So if you just want to be super scientific, just put one on the top left, one on the bottom right, because this is proving that from here to here, this connection is 1/2, right? Only one electron is being shared, and then here's your other 1/2. Only one electron being shared between these two connections, and then they'll come together. This is how he draws it, by the way. It goes like that. They come together and form one full pi bond, or it can just draw like I do. It doesn't really matter. Okay. Um, Also, I just want to point out, if you do draw it like this, and you say that only the top one is a pi bond, what about this guy? You're not labeling this. So, if you say pi bond, you're saying that there's two full pi bonds. That's wrong. Just put 1/2, okay? He didn't really say it in the notes, but this is technically more correct. Okay? Let's do angles now. So, from this chlorine to this carbon is your 120 angle. And then chlorine to chlorine is your 120. Okay, that's it. That is the hardest one. So please, please, please go over this. Um, you can change it up. Just swap out chlorine to like bromine. Try more practice. Okay, but this is the only way to do it, and this is the only way that makes sense. Okay, so remember, circle from right to left. Circle. When you circle, you're going to hybridize from right to left. Okay, very, very crucial. Okay, time for the next problem. Okay, this question is for molecular orbital theory, or just MO theory. And remember, for all questions, you must draw the Lewis structure of whatever you're looking at. You have to, okay? Especially if it's an ion. If the molecular orbital has an ion, it plays a huge role into knowing what you're talking about. Okay? So this is the Lewis structure of cyanide. Okay? Now let's check the formal charges. So the formal charge of nitrogen is 5, minus 3 lines minus 2 dots is 0. Carbon is 4, minus 3 minus 2 dots equals -1. So, a couple interesting things about cyanide. Cyanide, right, wouldn't you want the negative charge on the more electronegative atom? Well, this is the only case of cyanide that's polyatomic that doesn't follow that rule, okay? Because there's literally no way humanly possible to draw this Lewis structure. It only looks like this, okay? So just be careful. If there's absolutely no way that this doesn't necessarily make sense to you, it does. I promise. Just trust your gut. Okay. So I want to point out a few things first. So I'm going to refer to bacon. Probably heard of bacon. I'm going to say it, but just keep bacon in the back of your head, okay? So this is the skeleton of carbon and nitrogen, okay? Whichever is more electronegative, the whole thing gets shifted down, it being more electronegative, even though they are both part of bacon. So bacon just refers to the principal energy level, right? Where they both are at the same um, orbital splitting, but it's technically different because whichever atom is more electronegative, it gets shifted, right? So if this would be a straight line, right? This one's shifted down just a little bit. Same thing for the other ones. Shifted down just a little bit, and then shifted down just a little bit, okay? So this goes for everything, even though they're in the same principle, right? They're both in bacon. They still follow that rule. Whichever is more electronegative shifts. Okay, got it. So bacon refers to low pi. Okay, remember your pi bond has 2 splitting, and then your sigma, well, these are sigma. These are just 1. Okay, so you have a low pi. Your pi bonds is lower than your typical sigma bonds. Okay, so I want you to sing this melody. Okay, if it's bacon, it is pi sigma. Okay, there's an order. Okay, is, yeah, pi sigma pi sigma. If it's literally any other atom, it's high pi, right? So your sigma should come first. So it's sigma pi pi sigma, okay? Just follow that melody in case you forget what's what. So it's either going to be pi sigma or sigma pi pi sigma. Notice the top two never change. It's always going to be sigma on top, pi on the bottom for the top part. Okay? So know that melody. Pi sigma for bacon because you know it's low pi. Or sigma pi pi sigma. Okay? Refer to your notes for sigma pi pi sigma. Refer to your notes in case you have no idea what I'm talking about. Okay. So let's do carbon. So first off, remember how the box diagrams for the contour, right, is strictly valence? For your molecular orbital, it is everything, okay? So I'm not going to hold your hand. You should know how to do this, okay? This is for carbon, okay? This is your 1s, your 2s, and your 2p. Okay, for nitrogen, you should get, this is 1s, 2s, 2p. Oh, okay. Oops. It's this one, okay? So, remember how carbon was negatively charged, right? It gains one electron. So you're simply just going to add it. So that's the one it gained. Okay? So going back off that, that's the one that gained. So now you're going to count up all the electrons and then you're going to fill them in. So in total, you should have 2, 4, 6, 8, 10, 12, and then, 14. So you should have 14 electrons, and then you're going to put them into the respective energy diagram. So 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Notice how I placed it. 11, 12, 13, 14. Boom. Okay. So now let's label the middle. Okay. Here is your sigma 1s, sigma 1s star, sigma 2s, and your sigma 2s star. Now, I have a little acronym, so excited to show you. My acronym for the P's is oh my god, I'm a fake fan. I don't know how to spell her last name. Oh, thank you, autocorrect. Iggy Azalea. Okay. So this is how to memorize the pies. So it is your pi to py and your pi to pz. And if it's just one, right? If it's just one line, is considered as sigma. So it's your sigma 2px, right? Because that's the other one you don't have to know. Okay? Pi 2p y star, pi 2p z star, and that's your sigma 2px star. Okay? So Iggy Azalea, if you just literally memorize Iggy Azalea, you know that Iggy Azalea go together. Okay? Your Y's and your Z's are in the same energy level. They go together. And then the other one is just X. But it's just a sigma. Okay? A sigma 2px. So if you can memorize Iggy Azalea, you should label this correctly. Okay? And then boom. That's it. You're done. Okay? So let's do the electron configuration. So you're going to start from the lowest energy of a sigma 1s. There's 2 electrons. Sigma 1s star 2. Sigma 2s 2. Sigma 2s star 2. And then it's sigma 2px 2. And then it's your pi 2py 2, pi 2pz 2. Okay, so there is a very specific order. Okay, you're going to want to keep all your sigmas together and then all your pi's together. So notice it's not the direction of the energy, right? Where your sigma and then your pi's, your sigma should be over here. No, it's not how it works. You're going to keep all your sigmas together and then you're going to follow the order of like bonding orbitals, anti-bond. So right, regular, star, regular, star, regular, 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 because there's no stars. The stars are up here. But if these were filled up, it would be regular star, regular star, regular star, regular star. Okay? If you follow that order, you're gonna group up all the sigmas together and then group up all the pi's together. Yes, you must be like that, or you'll be wrong. Okay. So the formula for bond order is your 1/2, and it is your bonding electrons minus your anti-bonding electrons. This is simply just your stars. Okay, so I'm going to highlight them. Your bonding electrons will be orange, and your anti-bonding is green. So, your bonding electrons are 2, 4, 6, 8, 10. Okay, so this is just 1/2 of 10 minus anti-bonding is 2, 4. Okay, what's 10 minus 4? 6. What's half of a 6? 3. So this tells us a triple bond. And this checks out. Cyanide, a triple bond. This must make sense. Okay, it's a good way to check it, where you draw the Lewis structure first, and then see if it checks out. Okay, your magnetic properties is either going to be a paramagnetic or your diamagnetic. Okay, I hope you memorize this. Para, it wants a pair. Dia, it is partners that die together. So if every single electron has a pair already, they're gonna die together. Uh, so the answer is diamagnetic. Okay, that's it. That's just how to memorize it in case you want to know that acronym. Para wants a pair. Dia die together. That's it. Moving on to the next question. Okay, so for this question, you're going to compare a couple of species from each other. Okay, so there's a bunch of, he went over two different examples in the lecture notes. So there's three examples he can choose from. Okay, so find those in the lecture notes, and then here's another example. So this is comparing C2 minus versus C2 plus. Okay, so first I want you to draw C2. This is just regular, okay? No ion. So this is the carbon to carbon bonds. And notice how they're the same atom, so they're both in the exact same energy line. Okay, remember 1s, 2s, 2p. This is regular old chlorine. I like chlorine. Carbon. Did I say chlorine for the other ones? My bad. Oh, 6 electron. I'll just put 1. Okay. So, let's count how many total. So, 2, 4, 6, 8, 10, 12. 12 electrons total. Okay? Remember, carbon is part of baking. You're going to bake a low pi. So, you just follow like my little melody. Pi, sigma, sigma. Okay? Versus sigma, pi, sigma. Sigma, pi, sigma. Create like a little song, a little melody. It's kind of fun. Pi, sigma, or sigma, pi, sigma. Okay, remember these two don't change. So, what did I say? 12 electrons. Let me just 2, 4, 6, 8, 10, 12. Yeah, 12. Okay. 2, 4, 6, 8. Here's 10, and then 12. So you're going to label them. Sigma 1s, sigma 1s star, sigma 2s, sigma 2s star. Okay. Do y'all remember what these are called? Remember Iggy Azalea. This is how to know the difference between your pi's. Pi 2py, pi 2pz. Iggy Azalea. Okay, and you don't have to label all the other ones. Actually, I'm just gonna label it. Okay, this is your, if it's just one line, it is a sigma bond. So it's a sigma 2px. Okay, and then these are all your stars, because they're above. But you don't have to label them because there's nothing gonna go in them. Okay, so you're comparing and contrasting between one of the carbons gaining an electron and the other one of the carbons losing an electron. Okay, so if one of the carbons gains an electron, it goes up like this. So let's draw the bond energy order for this guy. So it's 1/2 of, let's count all the regular bonds. So it's 2, 4, 6, 8, 9. Okay. Minus your antibond, so all the stars, 2, 4, right? Okay. Just pull out my calculator real quick. 9 minus 4 is 5. Half of 5 is 2.5. Bam. Okay. Now let me just erase that. And then if you erase this one, right, there's your carbon that lost an electron. So now we're doing the carbon if it was positive. So this one's the one that's this one's the one that's negative, lost one. Now let's do the one that's positive. So your bond order is 1/2. Let's count them all up. So 2, 4, 6, 7. Antibond is still 4. So what is 7? 7 minus 4 is 3. Or wait. Oop. 7 minus 4, put it in my calculator wrong, is 3. What's half of 3? 1.5. Okay. Go back over here. So for the negative, it was 2.5. The positive is 1.5. Correct? Correct. Does this species exist? So in order for something to not exist, it must be 0. Okay? So if you get a bond order that's like 2.705, whatever, a bunch of freaking numbers, technically it still exists. Yeah, you're not gonna get it, like actually, but or if maybe it was like 0.0001 to like a bunch of freaking numbers, yeah, technically it still exists. It has to be a flat 0 for it to not exist. Okay? So even though it's a 0.5 of a bond, they both still exist. It just has to be 0. Okay? Now you're going to compare the length. So it is said that, so I'll go to bond length first. So the reason for bond length is that the higher the bond energy, the shorter the length is, right? So if 1.2 or 2.5 is higher, this one is shorter than the other guy, okay? Whichever is stronger, the higher the bond energy, the higher the strength. So this one is stronger. Okay, that's it. That's for that one. So, yes, you do have to draw the molecular orbital again, so just be careful. Remember my acronyms, remember my Iggy Azaleas, and you should be good. Oh, just one more thing in case he switches up the question. The higher the bond energy, the higher the bond dissociation energy, just in case. So if you ask which one has a higher dissociation, just look at the higher the bond order. Okay, just in case. Finally, the last question. This is quantum numbers, and I went ahead and already gave you the electron configuration of krypton. Krypton is a noble gas. You can find it on the top right of the periodic table. And you always give the quantum numbers of the last electron. So I like to solve this question first, just because, so I'm going to skip all the way to that. And remember, before you do anything, after you figure out the electron configuration, after you draw all the boxes, you absolutely have to draw the symbols. Okay? So remember, the middle of the box is 0. Then it's -1, +1. Okay? All these are middle boxes, so they all get zeros. -1, +1, 0. The very most middle is a 0. -1, -2, +1, +2. 0, -1, +1. Okay, great. So, your quantum numbers is that the first two numbers, right, this is your N, your L, your M sub L, and your M sub S. The first two quantum numbers, your N and your L, refer to the bottom of the box. So it is in, it is in the 4, and then a P start from 0 if S was 0. So if S is 0, P is 1. Then your last two numbers is the top of the box, or the symbol it's in. So it's in symbol number +1, it's just 1. And remember, I circled this last electron. That last electron is spinning down. So it's -1/2. Okay, those are the quantum numbers. Very simple. Just remember, first two, bottom of the box. Last two, top of the box. Okay, for all these other questions, you're simply just going to count. So, how many electrons have a M sub L -1? Right? Yeah, okay. That's an L. So, your M is the symbol at the top of the box. So, there's a couple -1 symbols. So, you're just going to count all those electrons in them. So, this has 2 electrons, 4, 6, 8. So, the answer is 8. How many electrons have L is equal to 2? So if L is referring, if S is 0, to get it to 2, so remember, 0, S, 1 is P, 2 is D. So out of all the D's, how many electrons are there? There's 2, 4, 6, 8, 10. The answer is 10. How many are N is equal to 4? So how many times did you write the number 4? Okay, you should have 2, 4, 6, 8 electrons. How many electrons have a positive 1/2 spin? So you're going to count all of the up arrows. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There you go. And that's quantum numbers. So, I was very brief, went over it, but I have a very detailed explanation of explaining quantum numbers in a previous video, so I will link that video in the description box below. And that is the entire exam 2 review. There is one other part of the exam review that's not on here, and you did have a quiz about it, so please study wavelength. Okay, refer to your notes. I will not be going over it. Please refer to your notes, okay? If you do have questions on it, see me in person, but I'm only covering the exam to review. But just in case he puts it under and y'all forget, don't tell me I didn't warn you, okay? You had a quiz about it where you're trying to figure out the wavelength and then it's possible color that's associated with it, okay? So refer to notes on that, on top of obviously this, okay? And that's it. That's the whole exam. Good luck.